kinematics of a differential drive car. Yes, I'm going to borrow the figure which I drew earlier. Okay. Now, here's the thing. When I'm trying to track a curve or the path, you usually choose some point on the system, right? For the manipulate, it's the end effector. Now, in this case, I have to make a choice. So what I'll do is I'll put a point, let's say over here, and call it some point P. And I would like this point P to track that curve. Okay? And this P can be anything, but it cannot be the point C. You'll see that if you try to put P as C, you'll run into issues, which will come when I show you the equations. You can only do it with a some point which is not at C, because when you invert the matrices or you do some matrix inversion, you'll see that the distance of P from the location of C is important. If it's 0, then you will not be able to trace the curve. So let's choose P to be at a distance of, so this is along the y-axis, let's call that Py. And this distance is along the x-axis. So let's call that Px. And remember that this Px and Py is going to remain constant, but it will change with the frame. So when this car goes here, this is still P, but its distance is still Py and Px. Okay, so our goal get P to track a reference curve. Okay, so let's see how to get that. In order to be able to do path tracking, I need to first figure out how does the point P evolve as the car moves around. So we know x dot c, y dot c, and theta. We need to find how P is related to c. So what we'll do is we'll write an expression for the point P in frame 0. So remember that this point in frame 0 is P0 in terms of the point in a frame 1, which is now the frame which is moved. Now it's at a different time t. So you've seen that we can relate them using the rotation matrix. Now you could write this as a homogeneous matrix, but you'll see that the constant part actually drops out. So we have this for P. We can also write something similar for C. Let's take the difference between the two. So just subtract one from the other. We have P0 minus C0 is R10, P1 minus C1. Okay. So here we note that P1 minus C1, this is the distance in frame 1. So the distance from, this is C1, this is P1. The distance from P1 to C1 is nothing but Px and Py. So we can write that as this is nothing but Px, Py. So I'm going to do is I'm just going to write it in terms of x's now. So we'll take the expression and expand it out. So we wrote on the left side P0 minus C0, which is nothing but XP minus XC0 YP minus YC0 equal to the rotation matrix, which we know is simply cosine theta minus sine theta, cosine theta. And then we saw that the right-hand side is Px and Py. Okay, so let's call this something. Let's call this 1. Okay, let's just write it as xp0 equals xc0 plus. So now, to get the next part, you just have to multiply px, py with that rotation matrix. So it comes out to be px cosine theta minus py sine theta. And then same for yp plus px sine theta plus py cosine theta. Okay, and what we were trying to do is we were trying to find a relation between P and C. And so this is the place where we differentiate the expressions. And that's where we'll get x dot C, and which we can then substitute with the equations of motion of the car. So differentiate with respect to time. So we have x dot P0 equals x dot C0 plus Px sine theta, theta dot minus Py cosine theta, theta dot. Y dot P0 is y dot C0 plus Px sine theta, theta dot plus Py. Sorry, this should be cosine theta minus sine theta. Okay, so we know that we already figured out what x dot C and y dot C is. So x dot P0 equals x dot C is v cosine of theta plus Px, set it as minus Px sine theta omega minus Py cosine theta omega, because theta dot is omega, and then y dot P0 equals v sine theta plus Px cosine theta omega minus Py sine theta omega. Okay, these equations are better written in terms of a matrix instead of writing as two equations. So I'm just going to combine them in a matrix form. So x dot P0, y dot P0 equals some matrix times v and omega. And we can fill in the dots by just looking at the things which are in that equation. So v gets multiplied with cosine theta. And then for the second part, we need to put these two things. So minus, let me just put it in brackets, px sine theta minus py cosine theta. That's my first equation. The second equation will have v times sine theta, and then px cosine theta minus py sine theta. Okay, so remember that x dot C, y dot C was very simple, v cosine theta, v sine theta. But the equation for t is a little bit more complicated. It has cosines and sines, and it also has omega, which was not there in C. And it also has the geometry, which is px, py, the point we chose. Okay, so now how do we do inverse kinematics with this equation? We want point P to trace the curve. And so this is something which I will teach a little bit later on. How do you, if you're given a differential equation, like say a manipulator, how do you control the manipulator? It's a method called feedback linearization. We'll talk in detail about it a little bit later, but just trust me on that. It works. It basically gives me tracking. The method is as follows. So we will use feedback linearization for inverse kinematics. Okay, so the method is basically x dot p0 equals to something. We just write this as x dot ref plus kp x ref minus xp0. Let's call that kpx, and then y dot p0 is y dot ref plus kpy. Okay, so let's see what this is. So this is just the controller. Okay, what I mean by controller is something which will enable us to track. The form of the equation which I wrote down here is the feedback linearization. It will be discussed in detail later. So what you do is you give it the reference velocity. So let's say that you want it to go in a circle. So that each point has a position, reference position, and also the reference velocity, which case of a circle is going to be tangential to that motion. For any curve, for that matter, is going to be tangential to the motion. So you give it x dot ref and y dot ref, and you also give it x ref, y ref, which is the position. And then this is basically something which you use a sensor to feed. So you need to know what the location of point P is in frame 0. Okay, like you have a sensor which measures that. Usually what you do is you keep track of point C as it is moving. And once you know point C, you can keep track of point P by using this formula. We basically use this formula, this or this one, same thing. So if you're given C, and if you're given theta and px, py, then you can compute xp, and that's how we keep track of p. Of course, we should know c. Okay, so let's just take this equation and put it in, let's call this equation 2. So we'll put this feedback control law, which is 3. So put 3 in 2, and we have cosine theta minus px sine theta minus cosine theta py sine theta px cosine theta minus sine theta by v omega equals x ref plus kpx x ref start minus x out of space. and y dot ref y ref minus y p0. So this comes from 3. So what we have here is let's call this whole thing as A, this whole thing as B. So we have A, let's call this X, AX equals B. In order to solve for X, which is V omega, we need to do A inverse B. And remember that everything here is known. Everything here is known. We're only interested in solving for X, which is our velocity. So how do we control the speed of the left and right wheel is coded in V and omega. So once we know V omega, we can then control the robot. But for that, we need to compute A inverse and A and then A inverse and then B. So I'll just give you the form for A inverse. And then instead of writing A and then inverting it, we'll just use that A inverse. And that will just make it slightly easier. So the A inverse comes out to be, so for a 2x2 system, it's kind of easy to get A inverse. So A inverse equals cosine theta minus py divided by px sine theta, and then sine theta plus py px cosine theta, then negative 1 divided by px sine theta, and then 1 divided by px cosine theta. And then b, as you know, is x dot ref plus kpx x ref minus x dot p, so x p0, and then y dot ref plus kpy y ref minus y p0. Okay, so I want you to note a few things here. First of all, you can see that in A inverse, you have px in the denominator. So if px equals 0, then A inverse will go to infinity. And so you cannot have the point P along with a 0 px distance. What that means for the differential drive car is that if you put, so P, this is P, you can have py equal to 0. So you can put this point on this over here. It should be not a problem. But if you move this point to here, so if you move this point here or here, anywhere on the y-axis, then you'll see that this A inverse will become infinity. And then you will not be able to get a solution. And that's because of the fact that this is somehow related to the fact that the car cannot move sideways. It can only move forward. So if the car is standing and if you're trying to go sideways, then it will tell you you need to go with infinite speed, which is clearly something which is not realistic, right? So px cannot be equal to 0. The second thing is, it turns out that this control law is kind of very powerful, that we can just ignore x dot ref and y dot ref, which you can just put 0 and you'll see that the control will still work. Okay, now that's not true for other systems, but for this system, you see that it actually works. You can just put that 0. You'll get better tracking if you have that non-zero, but if you put it 0, it will still work. This part is the feedback part. So if you're learning controls, the feedback is coming because of this term. And kpy by yref. So what feedback does is it figures out some error metric, right? In this case, the error is how close is xref to xp. Error in x. This is error in y. And it's saying that you want to try to keep that error as small as possible. So what you do is by controlling v and omega, you try to ensure that that error shrinks as much as possible. So this kp and kx, kpx and kpy are user chosen constants. User chosen, they call sort of called feedback gains. And so you can tune them. So typically you start with very small values and just keep ramping them up till you get a satisfactory performance. Okay, so with all that, we can actually go ahead and try to get the car to track a curve. I think I chose an astroid, which is this thing which looks like a square but rotated, but it's actually not straight lines. I'll show it to you in a bit. But the trick is we take these equations. Okay, let me just write down the recipe. I think it'll be useful when you try to understand my code. So before I show you the code, this is what we'll be doing. Here's the recipe for IK. First, compute or get xref, yref, and optionally x.ref, y.ref, right? I said it, you don't really need it, but if you want, you can get it. The way you compute it is you take xref, yref, the derivative. For a circle, xref would be, for example, a cosine t or a sine t for yref, right? For a more complicated curve, like if you do the homework, actually there's a PDF which I've shared, which gives you parametric equations for 50 curves, something like that. Second step is solve for, or rather, compute xp0, yp0 using the formula number is, so we'll use 1 to get xp0, yp0. We'll assume that we have some sensor on the car which gives us the position of point C. Okay, typically that is done by having what is known as the inertial measurement unit. Inertial measurement unit is a device which gives you, it gives you accelerations in the 3 directions. It gives you angular velocity in x, y, z direction. And some of them actually have a magnetometer, which gives you the magnetic, the direction of gravity, magnetism. And the reason why you need it is because you can use that direction in order to figure out which direction you're pointing at, because the Earth's north and south poles remain at the same place. So it's called a 9-axis inertial measurement unit. If you buy a 6-axis, it will not have the magnetometer readings. It'll just be accelerations and the gyroscope or the angular velocity values. So you'll get the xc, yc. Once you get that, and if assuming that you've kept a track of theta, which again comes from that magnetometer values, then you can compute xp and yp using 1. Third step is solve for v omega, which is, as I told you, A inverse B. Fourth step, so once we got V and omega, we can compute x dot C, y dot C. And then compute xc, yc. And then once you get xc, yc, you can compute use 1 to compute xp, yp. And then if everything looks right, then xp, yp should be x ref y. So, returning. So this is an asteroid curve. Play it again. We increase the pause. Put it to the parameters. Let's just change that to 0.2. I'll play a little slow. So that maneuver actually turning that much is kind of hard, I would say, but it can do it. I'll assign you a homework where you'll do this in MuJoCo. You can actually do this with a car. You don't have to write equations. You can just write the right control equations, not the entire simulations, and do it in MuJoCo. But it can also do that curve. I've been able to do that curve in MuJoCo. So what's going in this code is the fact that you need to, by the way, is it too long? It's about 160, 200 lines of code. So some point of time, the code starts, and you can just look by the function definitions. If there's a indentation, that means it's a function. So the code starts here. I get the parameters. I start the time 0, and I want to go for 10 seconds. I get the curve, which I said was step 1. Is to get the curve. That's the equation of the asteroid. And I need to do some conversions. I need to go from point P to point C, and point C to point P. So I wrote a function which will give me that. Given point P, gives me C, and so on. This is all the initialization, but this is the main loop, which basically takes the equations to account. So I've basically commented out, so you can probably understand better. So get xcyc, then get xpyp, then get the error. This is the thing I'm trying to control. Get it to 0. Then I find the errors by multiplying with the gain. I just keep the gain to be the same, or it's I think 100 or something like that. And then I take the A matrix and I multiply with this. This is actually the B matrix. So A inverse times B. Or actually, this should be called A inverse. Let's write it as A inverse. So okay, and then this is actually B. And then the 5th step is then you do Euler integration. Now, if you do it in MuJoCo, you don't really need to do that. You just set the command, and the MuJoCo will take care of the integration. And then I do some interpolations. That what happens if you do this, you'll get like too many points, and so we have too many points, and plotting it that way, it will slow down, because if you have too many points, the animation will go at stopping at every point. So I do some interpolation, so it's always so many points. So given a time span of 10 seconds, only do say 30 frames per second or 40 frames per second. That's what this function does. And then you just animate it. Okay, so I think it's self-explanatory. I hope it is self-explanatory. Another way you can learn about coding is to actually take somebody's code and then just start subtracting code out, just remove things. It will work or not work. If it when it works, it will do something different, then you get to understand a new part of the code. And that's another way to learn. Instead of writing code yourself, try to take somebody's code and subtract things out. And sometimes when I do this process, I find that the person who wrote the code has written some things to suit him and doesn't really suit me. So I will just modify that code to the way I write code. And that itself is like I think it's a good learning experience. When you see the code next time, it'll be more familiar than taking somebody else's code and just copy pasting it. Okay, so that's how you do inverse kinematics. I'm not sure about the homework for this, but I'm definitely going to have a MuJoCo homework where you will be actually doing a code. And I think that's kind of fun to do it with that than to do it with your own code, where you have full control over all the equations